Hey AP Stats kids, welcome to 7.2 Sample Proportions. I'm going to be a little bit all over the place today. I'm going to hit the big key ideas and let's just do it. What's learning targets? We're going to look at calculating the mean and standard deviation of a sampling proportion, p-hat, and interpret the standard deviation. We're going to determine if it's approximately normal. We've done this before. And we're going to use normal distribution to calculate. A lot of this is going to be a review. The only thing we're changing is a ratio, not an actual number. Okay? So sampling distribution of sample proportion p-hat describes distribution of values taken with sample proportion p in all possible samples, same size from same population. Big thing I want you to realize is p-hat is a proportion. Okay, what I mean by that is, stop it. P-hat, whoa, jeez. You'd think I would be good at this by now. So p-hat is going to be a percent, a proportion. Right? So it's going to be between 0 and 1. Right? And the only difference between that and before, when we found mean, the mean was like the average value. This is the portion of whatever from whatever. For example, when we look down here at this chart, these were pennies from the 2000s and 50 samples. Okay? This would have been, this 1p means in one sample of 20, 60% or 0.6 of the pennies were from the 2000s. Okay? As opposed to before, it would have been like 12 of the pennies were from it. This was one sample at 0.95 of the pennies were from the 2000s. So it's a proportion, not a mean. Okay, so it's like chapter 6, but it's proportions instead of means. Alright, I'm going to try this. Let's do this. My hair's like doing something. Nah, it's still weird. Alright. You can look at these and dissect them if you want. Whoa! And talk about shapes. For example, when n is small and p is close to 0, it's always going to be skewed to the right. Okay? So you're going to always have some values that are a little bit higher than the rest. Alright? Now, if n is small and p is close to 0, then it's skewed. I'm sorry, if n is small and p is close to 1, then it's going to be skewed left, because most of them are going to be to the right. There'll be a few outliers over there. And when it's close to 0.5, you're going to be skewed middle. It's going to look normal. Again, I'm going through this really quick. I don't think it's hyper important. I'm probably wrong. We're going to go through, holy smokes, I'm going to skip through a lot of this, because you're going to graph a lot of these anyways. Okay. Now, oh my gosh, this is kind of important. If the mean of the sampling distribution is equal to the population proportion, then it is an unbiased estimator of p. We're going to talk about that again, but I want to introduce it. So if your sample is the same as your mean, then it's an unbiased estimator. If it's not, it means your samples, there's something going on that takes them away from the population. Okay? Again, I'm going rapid fire through this stuff. We're going to do things with it in class. I don't want to spend too much time on it. Yeah, variability, the higher it is, the more it spreads. You guys can stop and look at this if you want. Here we go. Whee! I'm dizzy. Oh. Okay. I know that works. Alright, so let's take a look at this. The mean of a sampling distribution. Okay. This is tricky. Given a sample size of n from a population big N, the mean of p, oh my, the mean of the sampling distribution is your portion, whatever the mean portion is. Whatever the population proportion is. So if the population has a 20% chance of making a free throw and you take samples of size 20, you'd expect 20% of those free throws to be made. Should be your mean. Is it seem silly? Yeah, but the world's silly. Oh. Okay. Standard deviation is a little bit trickier. The standard deviation is P times 1 minus P, success times failure proportion, all divided by N. Okay? Now, as long as the 10% condition, remember where the sample is less than 10% of the total population, or equal to, then the measure typically varies by standard deviation about the mean. If that does not hold true, you cannot make a conclusion about the standard deviation. Okay? 10% rule is important here. Now, this last part, we saw it last chapter. We're going to see it again. We're going to see it a lot. If this is normal, as long as large counts is satisfied. So if n times p, your number in the sample, times the probability of success is greater than or equal to 10, and your number in your sample times your failure is greater than or equal to 10, then your distribution will be approximately normal. I'm going to become this person. Hey guys, I'm a student. Alright. So suppose 84% of students carry backpacks, okay? From class to class. And P has going to be a proportion of students in the sample who regularly use a backpack. So identify the mean. So A, our mean of P hat equals P. In this example, our P is 84%. 0.84. All right. B, standard deviation. So I'm going to do square root. Get out of here, keys. Square root of my 0.84 times 1 minus 0.84, all divided by number in our sample, 100, which I got to be 0.0367. Okay? Alright, let's cheat now. Let's see what they said. Yay! B, we got the same thing. Oh, geez, I forgot. We do have to assume that the 100 students are less than 10% of all the students in a large high school. Because if the 10% rule does not work, we cannot say anything about standard deviation. We don't know about it. Okay? So, in interpreting this, again, we have to do sample size. In a simple random sample size of 100, the proportion of students who use backpacks will vary, typically, by 0.0367 from the true proportion of 0.84. And it will be normal because 100 times 0.84 and 100 times 0.16 both equal over 10, so it will be normal. Okay. Now, what's neato is if the large counts rule holds, then we can use our calculators in normal CDF to find these proportions as well. Or we can make inferences based on it. Okay? So, if it's normal, they can ask us questions like, hey, what's the probability that the proportions will be between 0.2 and 0.8? Then we can use normal CDF. We have to use normal CDF to find the range, proportion of ranges. Okay? Let's see an example. I'm going to wear this sweater. Look at it, I'm wearing a red sweater. Oh my gosh. What an asinine fool I am. So they're going to take a simple random sample of 1,500 first-year college students. 35% attended college within 50 miles of their home. What's the probability that in a random sample of 1,500 students that it'll be within 2 percentage points of the true value? All right, I'm going to graph it. Boom, I graphed it. Now, is n times p and n times 1 minus p over 10? 0.35 times 1,500 is much larger than over 10. Okay, and there's and 1,500 times 0.65 is way over 10. So we're good. It's normal. Now we have to think about this. 1,500 students is less than 10% of all freshman students. Agreed? Okay. So now, I'm looking for, my mean's 0.35, right? What's 2 percentage points away from the true value? That means I'm looking for from 0.33 to 0.37, right? Boom, right here. So now, because I know that's normal, I can use normal CDF to find that. My lower bound's 0.33, upper bound's 0.37. My mean is 0.35. I don't have a standard deviation though, right? So I have to find my standard deviation first. So I'm going to do square root of p. That's 35. That's 35 times 1 minus p all over my n, right? When I calculate that out, I'm going to cheat here and see what I got there. I got 0.0123. And when I plug this into my calculator, I get, drum roll. So I want drum roll. 0.8969. Is my face in the way? Nope. Cool. All right. So let's check ourselves and see if the book got the same thing. Again, I don't own this. Yes. 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 No, I didn't do it that way. I did that way. Yeah. Okay. So, we should be good. I hope you guys have a phenomenal day.